All right, so welcome to Physics Essentials video 2.3. We're going to be learning about Newton's second law. So Newton's second law. First of all, Newton's first law tells us what an object will do if the net force on the object is zero. All right, specifically, if the net force is zero, then the acceleration is zero and the velocity is constant. That's what we've spent the last day or two talking about. Okay, that's what the first law says, is that these three statements are equivalent. If one of them is true, they're all true. All right, so it turns out that Newton's second law tells us what the object will do if the net force is not zero. All right, and we already know that if the net force is not zero, then the acceleration is not zero, which means the velocity is changing, right? All right, so Newton's second law takes us a step further than that, and it tells us that if the net force is not zero, it tells us how to calculate the acceleration. We know it's not zero, but what is it? Well, that's what Newton's second law tells us. All right, so Newton's first law focuses on what happens if the net force is zero. Newton's second law focuses on what happens if the net force is not zero. Okay, so here's Newton's second law. It says that if you want to calculate the acceleration of an object, you can do that by taking the net force acting on the object and dividing it by the mass of the object. Okay? Algebraically, we can rearrange this equation. Usually the way that you'll see this written in textbooks is people will say net force is mass times acceleration. So keep in mind that this equation and this equation algebraically are the same thing. This is what you'll see in most books. I tend to believe that this is sort of more useful for students for reasons that'll become clear once you learn it a little bit better. Okay, so those are the two most common versions of the equation. I should probably finish it and just comment that you can also calculate the mass if you ever had to, although it comes up rarely. Okay, so these two equations here that have boxes around them are Newton's second law. So if somebody says, what's Newton's second law? That's it. It's that equation. Okay. Notice up here at the top of the screen, I've written down what the stuff is, right? A is your acceleration. Remember, we're always going to measure acceleration in meters per second squared. Okay, the squiggly F, net force, is always going to be measured in newtons. And finally, this M is new. M stands for mass. All right, the mass is the mass of the object measured in kilograms. And we really have not talked about mass at all. So let's talk about mass. All right. When you take chemistry, teachers tend to teach that mass is a measure of how much matter makes up an object. Okay. For the most part, when you measure mass, you're sort of counting molecules or atoms or tiny little particles. And the more tiny little particles make up your object, the more mass it has. Okay. Now, because of that, it turns out in physics we say that all mass has what's called inertia. Okay, so in physics, the definition that we give of mass is a measure of an object's inertia. Okay, so these are two different definitions for mass, but they're both sort of equally good. All right, to be 100% honest with you, in most cases, I tend to prefer the chemistry definition. But for our purposes today, we need to talk about this idea of inertia. So here's what you need to know: an object that has more mass has more particles, more matter in it, more particles making it up. And because of that, it has more inertia. So then it raises the question, well, what the bleep is inertia? So here's our definition of inertia. All right, this is super important. Okay, so inertia is an object's resistance to a change in motion. It's a resistance to a change in motion. Okay, so for this to make sense, it probably makes sense to talk about a couple examples here. So why does mass measure an object's resistance to a change in motion? So imagine that your left and right arms are equally strong. If you push an empty shopping cart with your left arm and a full shopping cart with your right one, which one's going to move less? Okay, think about that. If you're pushing two shopping carts, you get an empty one and a full one, and you push them both, the one that's full is going to move less, right? The full one moves less because it has more mass. It has more resistance to a change in motion. All right, the full one resists a change in motion more because it has more mass. Okay, if you were blind and could not, see which shopping cart was full, you could push them and figure out that the one that's harder to move is the one that's full. Okay. All right, now similarly, imagine that the two carts are rolling at you, right? You're hanging out in the parking lot and these two shopping carts are rolling at you, and you want to stop them, right? So which one's going to be harder to stop? Well, again, the full one is going to be harder, right? Because it has more mass. It has more resistance to a change in motion. So the full one resists a change in motion because it has so much mass. All right? So basically, here's what Newton's second law says. The first part is kind of intuitive, right? Here, well, let's write down the equation first of all. Here's Newton's second law. Newton's second law says acceleration is net force over mass, right? Okay, the acceleration of your object depends on the force and on the mass. All right, and so it tells us two things. It tells us the harder you push something, the more it'll move. In other words, the more net force you have on your object, the more it's going to accelerate. That's totally intuitive. The harder you push something, the more it moves, right? Okay, that's the first half of Newton's second law. Okay, the second half of Newton's second law says that when you push something, the more mass it have, I can't talk today. The second part of Newton's second law says that when you push something, the more mass it has, the less it will accelerate. Okay, in other words, as your mass increases, your acceleration decreases, right? That's the full shopping cart versus the empty one. If you've got a big mass, it's going to give you a smaller acceleration. Okay? So that is Newton's second law. So let's do some examples here. Okay? So it says find the acceleration if Roy pushes each of the boxes from rest. So that's important because it's telling us that our initial velocity of the box is going to be 0. He's pushing it across a frictionless floor with the given force. So this is basically just some quick calculations. So for the first one, we know the mass of the box and the force of Roy. So you've got your box. The mass is 4 kilograms. I'm always going to start writing the mass of the object inside the box. That's new. You got to add that to your drawings. Label your force of Roy. It's 12 newtons. Since that's the only force, our net force is going to be 12 newtons, right? So to find the acceleration, it's net force over mass, right? 12 newtons, 4 kilograms. And when you divide this, you end up getting 3, and it turns out that the units work out to meters per second squared. I'm not going to go into why that is right now. If you take the regular physics class, I'll stress that a little bit more. But for the purposes of this class, just know that everything here is metric. And in the metric system, we measure acceleration in meters per second squared. And so that's what we get. Okay? Now, in part B, everything is the same except we're pushing with twice as much force, right? Look, we're pushing with twice as much force. So you're going to have the same box, 4 kilograms. But now the force of Roy is significantly bigger. It's 24 newtons. So think about this before we calculate it. If you push something harder, is it going to move more or less? It's going to move more, right? So our net force is 24 newtons. To find the acceleration, it's net force over mass. So now we've got 24 newtons pushing 4 kilograms, and you get 6 meters per second squared. So look, 12 newtons gave us 3 meters per second squared. Twice the force gave us twice the acceleration, right? Okay, that's called a direct proportion. You've got twice as much force, you get twice as much mass. Twice as much force, twice as much acceleration. I hope I didn't say that before. So again, twice as much mass in this, oh geez. Okay, you have twice as much force, right? And the result is twice as much acceleration. Finally got that right. Okay, now in example C, we're going back to 12 newtons, but now we've got a bigger box, right? So look, now we've got an 8 kilogram box being pushed with 12 newtons. So compare this with part A. In both of them, you're pushing with a force of 12 newtons. The difference is the mass. So which of these two boxes would you expect to move more? Isn't the lighter one going to be easier to move? Acceleration is net force over mass, right? So we've got a 12 newton force pushing an 8 kilogram box. So when you divide this out, you end up getting 1.5 meters per second squared. Okay, so look, we've got twice as much mass, and it gave us half as much acceleration. Okay. So that is that. I'm going to not worry about example D. It's basically more of the same. What you end up finding is that you have twice as much force pushing the box, but you also have twice as much mass as example A, and so you end up getting the same acceleration. Okay? All right, I think the last thing that I want to talk about here, well, this is talking about stuff that I already talked about, so I think the last thing I want to do is an example where we're calculating the net force. All right, so let's do this. Suppose you wanted to push a 6 kilogram box at, I don't know, say 3 meters per second squared. Let's find the net force, find the force required. Okay, we're going to assume there's no friction or anything. We're going to keep things simple. Okay, so if you flip back a little bit, we learned that you can calculate net force by multiplying the mass by the acceleration. So that's all we're going to do here. In this example that I just wrote, oops, what do we know? We know that the box is 6 kilograms. That's the mass of the box. We know the acceleration of the box is 3 meters per second squared. And the question is, how much force do we need? Well, net force is mass times acceleration. So the box has a mass of 6 kilograms. Acceleration is 3 meters per second squared. Multiplied out, your net force is going to be 18. Because it's a force, it's newtons. And so if you assume there's no friction, in order for the net force to be 18 newtons, that means that the force you would need would have to be 18 newtons. Okay? So that is Newton's second law. Also, probably really, since I got a minute here, keep in mind that if you had more mass, you'd need more force, right? Like if this was 10 kilograms, it would mean you'd need more force. And similarly, if you wanted more acceleration, you'd need more force, right? Okay. So there you go, Newton's second law. The end.